I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In today's video lecture, we will discuss on the polar plot. In today's video, we will specifically discuss on what is the frequency response, the polar plot, how to state the polar plot, and examples. So, first we need to learn what is the frequency analysis or frequency response. Previous video we have started with the time domain analysis, but in time domain analysis we have used the standard input signals such as impulse, step, ramp, and those standard input signals were used to study the performance of the control system. But using the different input signals, the extraction of the transfer function is very laborious process. So here we will discuss on the frequency response, and in frequency response or the frequency analysis, it is much easier to obtain the transfer function. The frequency response of a system is the response of the system for sinusoidal input signals of various frequencies. Now we know that sinusoidal input signal is represented by R of t, and mathematically it is A sin omega t, where the A represents the amplitude or the magnitude of the signal and omega is the frequency of oscillation. Now, if the RT in time domain is represented by A sin omega t, then in frequency domain, after taking the Laplace transform of this RT, we are getting the RS. RS is nothing but the Laplace transform of RT, and it is equal to A into omega by S square plus omega square. So, the frequency response has some advantages on the time response. So, in frequency response, the design parameter adjustment of the closed loop system for specified closed loop performance can be carried out easily in frequency domain rather than in the time domain. Whereas in time domain, the effect of noise disturbance cannot be easily visualized, which is very much clearly visualized in this frequency response, as well as there is a correlation between the time and frequency domain performance of a linear system that can easily be predicted using the frequency domain specifications also. And the most important is the frequency response is not limited to the lower order system. That means in case of the higher order systems, we can easily apply the frequency response analysis. So now the polar plot comes, and the polar plot is a plot of magnitude versus the phase angle in the complex plane. That is the locus of the magnitude traced by the phasor by varying the frequency omega from 0 to infinite. And the most advantage of the polar plot is that it can give the behavior of the system over the entire frequency range in a single plot. Now, to find out the polar plot, we need both magnitude and phase angle of the G of S. And here, S will be represented by sigma plus j omega, where sigma is the real part and j omega is the imaginary part. So, to specify the behavior of the system to a sinusoidal input at a particular angular frequency omega, that is the frequency response of j omega. So, both magnitude and the phase are actually the function of the input frequency, and therefore, when we are varying the omega, So both magnitude and phase angle are varying respectively. So here this is the S-plane where x-axis represents the real and y-axis represents the imaginary part of, and the angle between these two is phi, and this is the magnitude. So to draw the polar plot, we need to take care of both the magnitude, that is mod of Gj omega, and the phase angle phi, that is the angle of Gj omega. So next, how to draw the polar plot. So to sketch the polar plot of Gj omega for the entire frequency range, that is from 0 to infinite, first we substitute the S is equal to J omega in the open loop transfer function. And we need to express the magnitude and phase angle of G of J omega, H of J omega. So now, so the sinusoidal wave is varying from 0 to infinite. So if it has higher frequency or lower frequency, then omega is varying from the 0 to infinite also. So when omega is 0, that will be the starting magnitude and the phase of Gj omega is G omega. So we need to find out the starting magnitude and the phase by substituting omega is equal to 0. And when omega tends to infinite, that will be the ending magnitude and the phase angle of G of J omega is J omega. So we need to find out the ending magnitude and the phase by substitute omega is equal to infinite in the magnitude relation and the angle relation. Next we need to check whether the polar plot intersects the real axis or not. And next we need to find out whether the polar plot intersects the imaginary axis or not. So to find out these 2 points of intersection, first we need to rationalize the function into real part and imaginary part. By dividing these two real part and imaginary part, when we are going to find out the point of intersection with real axis, then we need to make the imaginary term of Gj omega is J omega equal to 0. So after getting that, the imaginary term equal to 0, we can find out the value of omega, and from that we can find out the point of intersection with the real axis. In the same manner, to find out the point of intersection with the imaginary axis, we need to take the real term of Gj omega and that term will be equal to 0. After that comparison, we will get the value of omega and then we can find out the point of intersection with the imaginary axis. So in case of polar plot, this is the real part or the sigma part and this one is the J omega, and we need to take the angle negative in the clockwise direction. So this is sigma f equal to 0 and the angle phi is equal to 90 degree, then minus 180 degree, then minus 270, and again minus 360. So minus 360 and 0 is the same line. And the angle will be taken in the positive in anti-clockwise direction. So we are considering throughout this lecture, angle is taken negative in the clockwise direction. So we will getting that 0, minus 90, minus 180, then minus 270. So now let's take an example. Here I am considering one first order system whose Gs is given as 1 by 1 plus S tau. And here this tau is the time constant of the system. So as per the rules, first we are going to put S is equal to J omega. So G of J omega becomes 1 by 1 plus J omega into tau. So to rationalize, we have to multiply both the numerator and the denominator by the conjugate of the denominator. So it becomes the 1 minus J omega tau by 1 plus omega square tau square. So we can divide it into real part and the imaginary part, where the real part becomes 1 by 1 plus omega square tau square and this one is the j part or the imaginary part, that is minus omega tau by 1 plus omega square tau square. Now, the mod of Gj omega can be calculated by using the formula x plus Iy. The mod of this x plus Iy is root over of x square plus y square. So, in the same way, this is under root of real part square plus the imaginary part square. So, it becomes 1 by root over of 1 plus omega square tau square. So, this is the magnitude. Next, we need to find out the phase angle. Now, if a complex number is there, x plus Iy, then the angle becomes tan inverse y by x. So, in the same manner, the angle phi is calculated here, tan inverse the imaginary part, that is minus of omega tau by 1 plus omega square tau square, divided by the real part. So, it gives tan inverse minus omega tau divided by 1. So, to start the polar plot, first we need to take this magnitude and this phase angle, then omega will be varying from 0 to infinite. So, for omega equal to 0, we need to calculate the magnitude and phase angle, as well as when omega is equal to infinite, then also we need to calculate the magnitude and the phase angle. So, when omega equal to 0, that means this starting point, if we put the value omega equal to 0, then we are getting the magnitude starting from 1 and the phase angle becomes 0. So, this point, one point is located on the 0 degree angle. Next, we need to find out the value of omega. When omega equal to infinite, we need to find out the value of magnitude and the phase angle. And by putting the omega is equal to infinite over this magnitude relation and this angle relation, we are getting that magnitude becomes 0 when omega is infinite, and the phase angle that it becomes minus 90 degrees. Now, we are putting the value omega is equal to 1 by tau. So, when omega is equal to 1 by tau, then the magnitude becomes 1 by root 2 and the phase angle becomes minus 45 degrees. So, let us draw the polar plot. So, to draw the polar plot, first we need to draw the real axis and the imaginary axis. So, this is the sigma part or the real axis part, and this is the j omega part or the imaginary part. Now, when omega is varying from 0, the magnitude is 1 and the phase angle is 0 degree. So, we need to take the 0 degree line, that is the reference line, and on this 0 degree reference, the magnitude will be taken as 1. So, this length from 0 to this length is considered to be 1 here. So, this one is unit length. So, this magnitude is 1, phase angle of this point is 0 degree, and here the omega value is equal to 0. Next, we need to take another point, that is the 1 by root 2, that is when the omega value is 1 by tau. So, 1 by root 2 value is, we are getting value when the phase angle is minus 45 degree. So, we are taking this minus 45 degree angle, and above this angle, we are taking the point 1 by root 2. So, this point is here, and here the omega is 1 by tau, where the magnitude is 1 by root 2 and phase angle is 45 degree minus. So, when omega is infinite, then we are getting the angle is minus 90 degree. So, this one imaginary line, that is in this line is the minus 90 degree line, and in this minus 90 degree line, the magnitude is 0, which represents this point. So, next we are going to join this 1 magnitude at 0 degree line, then 1 by root 2 magnitude at minus 45 degree line, and at minus 90 degree the magnitude 0. If we draw this, then we are completing the polar plot of the transfer function Gs equal to 1 by 1 plus is tau, where tau is representing the time constant of the system. So, in this way, we can easily plot the polar of the transfer function. Let us take another example where the open loop transfer function is given as GSH is equal to 5 by S into S plus 1 into S plus 2. So here also the HS is 1 actually, and it is a unity negative feedback. If nothing is mentioned, then we will consider the feedback is unity negative feedback. So here we are putting S is equal to J omega. So G of J omega and H of J omega becomes 5 by J omega into J omega plus 1 into J omega plus 2. Next, we need to find out the magnitude, and magnitude can be calculated as 5 divided by each of the term is imaginary term. So we will compare each term with x plus iy. So the real part of J omega is equal to 0. So it becomes root over of 0 square plus omega square, which is actually gives the omega. So that's why for J omega, the magnitude is omega here. For this term, it will be root over of real part square, that is 1 square, that becomes 1 plus omega square. So it is root over of omega square plus 1. For the next term, the real part is 2, so root over of 4 square plus omega square. So that is written as root over of omega square plus 4. Next, we need to find out the phase angle of the open loop transfer function, that is angle of Vj omega, Hj omega. So now for the angle, this is the 0 plus J omega. So if we consider x plus iy, then the angle becomes tan inverse y by x. So here the imaginary part is omega and real part is 0. So it becomes tan inverse omega by 0, that is infinite. And tan inverse infinite means the angle will be minus 90 degrees. And each of the terms will contribute the angle in minus because all these terms are located at the denominator. If this term is located in the numerator, then it will give the angle contribution in plus sign. So here for 1 by j omega, the angle is minus 90 degrees. And for 1 by 1 plus j omega, this angle is tan inverse omega by 1, that means actually tan inverse omega. And for this j omega plus 2, that is tan inverse omega divided by 2. So in this way we can calculate the phase angle. Next we need to make a table where the frequency omega is varying from 0 to infinite, and we need to calculate the magnitude and phase angle at the frequency equal to 0 and at the frequency equal to infinite. So when the omega equal to 0 and we are putting the omega equal to 0 in magnitude and phase angle, then we are getting magnitude is infinite and phase angle becomes 90 degrees, whereas when the frequency is infinite, then the magnitude is 0 and the phase angle becomes minus 270 degrees. So based on the starting and the ending point of the polar coordinate, we need to draw the polar. And for minus 90 degree, so this one is the minus 90 degree line, and in this minus 90 degree the magnitude is infinite. So that's why it is coming from this side. So it means that it is coming from the infinite point on the minus 90 degrees. And then it goes to minus 270. This line represents the minus 270 because in clockwise direction, if it is 0, then minus 90, minus 180, then minus 270. And at minus 270, the magnitude is 0, that is its origin point. So this curve will start from infinite position of minus 90 degrees, then it goes to the 0 magnitude of the minus 270 degrees. So this one is the complete curve. Now this curve will intersect the imaginary real axis in some point. So next we need to find out this point of intersection with the real axis. So the phase angle corresponding to this negative real axis is actually minus 180 degrees. So we can equate the phase angle minus 180 degree with this angle criteria. So if we do that, then we can calculate the value of omega by comparing this is equal to minus 180 degree, and then after getting the value of omega, we can find out the magnitude. So by comparing minus 180 degree with this angle criteria, we are getting omega equal to root 2. So if we substitute this omega equal to root 2 in this magnitude relation, then we can find out that m equal to 0.83. So as this m represents the magnitude, that's why the sign is positive here, but it is actually located on the left hand side of the s-plane, so it becomes minus 0.83. So this minus 0.83 is the point of intersection with the real axis, and this orange line represents the complete plot. So these are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.